All right, in this video, we are going to go over our Unit 5 free response questions as a review for our Unit 5 test. So, FRQ Part A, number 1. First of all, very important to note that it mentions that we need a graphing calculator. So not only do they say like, hey, you get a graphing calculator, they say that that graphing calculator is required. And I will walk you through exactly what you would use it for. So, number 1, it gives us couple pieces of information. It tells us that f prime of 1 is equal to 0, and then they give us the second derivative is x squared times cosine of x squared plus pi, keeping in mind that pi is just a constant, and it defines it on this restricted interval right here. And then it mentions that f is twice differentiable. That means that f prime exists everywhere. That means that f double prime exists everywhere on that specific domain that they mentioned. So they give us this info, and then we've got a few different pieces that we need to answer. So letter A, and I'm hoping that you've got these questions in front of you because I don't want to actually write everything down, but I will read the questions. So letter A says, on what open intervals in between -1 and 3 is the graph of f concave up? Okay, so we'll write some little notes here. So where is f concave up? That is what they're asking us about on the open intervals contained in this interval right here. So when we are asked a question like that, we want to go to our handy little chart. So they are asking us when f is concave up. Now, pay attention to what they gave us. They gave us f double prime. So we compare the column that we're looking for with the column that they gave us. So f is concave up whenever f double prime is positive. So that is what we are looking for. We want to know when f double prime is positive. And we have a calculator. You are not going to set this equal to 0 and make a sign chart by hand. What we are going to do is graph this equation, look at it, and tell me when it's positive, meaning like when is it above the x-axis or when does it have a positive value. All right, so we are going to go into a graph page on our document. We are going to plug in that equation. We're going to plug in x squared multiplied by the cosine of x squared plus pi. Okay, we're going to do a quick confirmation that we're in radian mode, which we are because there's trig involved. So hit enter. So this is what our graph looks like. I'm going to zoom in for you, and you want to make sure that we're matching the interval that they gave us. So you are going to change the window. So I press the menu key. We're going to change the window. If you're on an 84, you have a window menu like up along the top right under the screen here. And then you can select window settings, and we are going to change the x values to the x values that they gave us. So -1 to 3. So now we're just looking on that interval right there. So we want to know when this graph, this is the graph of f prime, when it is positive or above the x-axis. So we have this interval right here, and then we also have this interval right here. So in order to find those values, we don't ever just guess. All right, so if you're on an 84, there's a button up along the top that should say calc, like you're going to hit second and then calc, and then you can figure out where the intersection points are because we want to know this point and this point and this point. Those are our x-intercepts. So if we can calculate the x-intercepts, then we'll be able to write down those intervals. So menu, and on this calculator, we're going to do analyze graph. Like I said, if you're on an 84, there's a button up here that says calc. You'd have to press the second button first. And then we're going to select the option that says 0. So on the 84, you would literally move your cursor to the left and to the right when they say lower bound and upper bound. This, we can just arrow back and forth. So click somewhere to the left of the first intersection point, press down, and then arrow over somewhere to the right and press down. So it kind of catches that x-intercept. In AP Calc, you always want 3 decimal places. So we are going to say 1.253. So that's the lower bound. And I like interval notation, so I'm going to write it like that. And then next piece, we do the exact same thing. Menu, analyze graph, 0, and we're going to catch that second x-intercept. So click somewhere to the left, and then somewhere to the right. And we can see barely it says 2.1708. So 171 or 170, whether you round or truncate. I personally am a rounder, so I'm going to write 171. So in between those two x values, f double prime is positive, which means f is concave up. And then we move to another interval. We want to see where this interval starts. Now we want this third point right here. So menu, analyze graph, 0, and we go from the left to the right and capture that one final point. And they're all overlapping here, so it's kind of hard to see. But this is 2.802. And the next digit is a 4, so it's 802 no matter what. So 2.802. And the question specifically said to just, whoops, I am way too zoomed in here. Specifically said to stay within this interval, so we only go up to 3. It extends farther than that, but we are restricting our domain to these points right here. So these are the intervals where f double prime is positive, which, remember, if we look at our chart here, that means that f is concave up on those intervals. Letter B. Letter B says, does f have a relative min, a relative max, or neither at x equals 1? Justify your answer. Okay, so f, max, min, and then we'll talk about neither. So if the second derivative was changing, then that would mean, if the first derivative was changing, then that would be a max or min. So here's what we're gonna look at. We know this, okay? They asked about x equals 1. We know that the first derivative is equal to 0. That makes this a critical point, okay? So x equals 1 is a critical point. We know that for sure, and that's because the first derivative is equal to 0 there. That's the definition of a critical point. So now what we're gonna bring in is the second derivative test. Okay, so this is something that's super important. We plug that point into the second derivative. What that will tell us is the shape of the graph, whether the graph is concave up or concave down. So we know the slope is 0 there. Okay, so that might mean that it's a maximum like this, it's a minimum like this, or it could be one of those weird situations where it kind of levels off and keeps going like this, or decreasing. So we want to figure out which one it is. The reason we want to bring in the second derivative is something called the second derivative test. If our second derivative makes the graph concave down, our critical point would be a max. If the second derivative makes our graph concave up, that critical point would be a min. So we want to know this value, and because we have a calculator, we can just plug that point right in. All right, so I'm going to look at a calculator page, and we're going to plug it into this function right here. So x squared becomes 1 squared. Multiply that by the cosine of x squared, or 1 squared, plus pi. Okay, so make sure it looks exactly like your equation does, and then go ahead and press enter. Confirm that we are still in radian mode. We are. So we get this value right here. Okay, oh, there we go. Negative 0.540. The value itself does not matter. The important part is that it's negative. So negative second derivative means that your graph is concave down. So what we know is that our graph is concave down and the derivative is equal to 0. That makes this a maximum. Okay, so it says to justify your answer. So we are going to say that x equals 1 is a relative maximum because f prime of 1 is equal to 0. Remember, that's what makes it a critical point. And f double prime is negative, which makes it concave down. So we don't have to explain any more than that because this is just the result of the second derivative test. All right, so that's part B. Flip your page here for part C. Part C says use the mean value theorem on the closed interval from -1 to 1 to show that f prime of 1 cannot equal 2.5. Okay, so we're going to show that f prime of -1 cannot equal 2.5. So mean value theorem on that closed interval. Okay, so we are going to check f prime. We want to find that mean value theorem, right? So we have f of 1 minus f of -1 over 1 minus -1. Okay, so we're going to get those values. So let's see, it gives us, you know what, it doesn't even give us f, so let's see. We are going to have to use f double prime. All right, so let's work backwards this way. All right, so we're going to use the MVT on the first derivative. Okay, so we set this up. So here's what we know. All right, so we know that f prime of 1 is equal to 0 minus, and then we don't know what this value is, over, and then 1 minus -1 is equal to 2. All right, so we've got that information. We have 0 minus f prime of, whoops, -1 right there. So these are the values that we're trying to figure out. And we are trying to show that it cannot equal 2.5. So the idea behind the mean value theorem is if we figure this out, then at some point that should be equal to the slope. That should be equal to the second derivative, all right? So this guy right here has to be equal to the second derivative at some point, all right? So showing that f prime cannot equal 2.5 is the same as saying if we plug a 2.5 in here, it can't be any value of f double prime. All right, so we have negative, throw the 2.5 in here, divided by 2. We're saying that like this just can't possibly work out. And the mean value theorem would show that that has to work out. So here's what we're going to show. This ends up being -1.25, which we are saying cannot possibly equal f double prime at any point. So let's look at that graph. Let's bring that graph back that we had from earlier. So this right here, so somewhere on this interval right here, our second derivative is supposed to come out to be this. All right, so now if we look at that interval, let's change our window a little bit. So now we want to look between -1 and 1. Okay, so we zoom in, we look at those values. At some point, this is saying that f double prime must have been equal to -1.25. So here's -1. -1.25 would take you down underneath that graph where f double prime never hits. So if f double prime is never equal to 1.25, -1.25, we can trace this backward to say that f prime couldn't possibly have equaled 2.5. Because if it did, then this would have worked out. Because the MVT always works as long as your function is continuous and differentiable, which we know that it is. All right, so this can't possibly work out. So therefore, f prime of -1 cannot equal 2.5. Okay, because if this were true, then this would be true, and this would be true, and this would be true, and you can kind of trace that all the way back. And the mean value theorem doesn't fail as long as your function is continuous and differentiable. All right, so if we knew that this was true, then that would say that this must have been true if we plug in a 2.5 here. And since this doesn't work out, then this can't possibly be true. So kind of a very bizarre interpretation of the mean value theorem, but the important part is that here's what the mean value theorem says. If we do this slope formula like this, at some point, your derivative is going to be equal to that average rate of change as long as your function is continuous and differentiable. So very unique interpretation of that MVT, but it does hold up here. All right, letter D. Does the graph of f have a point of inflection at x equals 0? Oops, D. All right, so point of inflection at x equals 0. That is what we want to know. So let's look at our 3-column chart again. Does f have an inflection point at x equals 0? They gave us f double prime. So if f double prime has a sign change at x equals 0, that is the exact same thing as saying that f has an inflection point. Okay, so if f double prime has a sign change at x equals 0, then we will know that f has an inflection point. So let's look back at that graph one more time. Okay, so we see right here, here's x equals 0. We are going to go back to our original window between -1 and 3, because that's what they defined it as. All right, so you can see right here, it is equal to 0 there, but it's not a sign change. it's below the x-axis, it hits 0, and then it goes back below the x-axis. So this is f double prime. F double prime is not exhibiting a sign change at x equals 0. It's negative and then goes right back to being negative. So no, this is not an inflection point because f double prime does not have a sign change. Okay, so we are going to say no, and that is because f double prime does not change sign at x equals 0. So notice our handy little chart has been very, very essential in answering all of these questions. Okay, so that was FRQ Part A, number 1. I'm breaking these up into 3 separate videos so it's not an overload.